using LinearDiophantineWP equations to solve word problems. So first I'd like you to pause the video and read this word problem. So in this problem, we need to find out how many US dollars and how many Canadian dollars she had. So we'll let X equal the number of US dollars, and we'll let Y equal the number of Canadian dollars. The equation then we have is 111 times X plus 85 times Y equals the 14,832 yen that she received. The first thing we need to do is use the Euclidean algorithm to find the GCD of 111 and 85. We need to assure that that GCD divides evenly into 14,832. If it does not, then there is no solution to this problem, or no integer solutions to this problem. So we've got 111 equals 1 times 85 plus a remainder of 26. We've got 85 equals 3 times 26 plus a remainder of 7. 26 equals 3 times 7 plus a remainder of 5. 7 equals 1 times 5 plus a remainder of 2. 5 equals 2 times 2 plus a remainder of 1. And finally 2 equals 2 times 1 plus a remainder of 0. So the GCD is 1, and 1 does divide evenly into 14,832. So we know we have a solution. So as before, to set up for the extended Euclidean algorithm, we're going to solve each one of these equations for the remainder. So 26 is equal to 111 minus 1 times 85. 7 equals 85 minus 3 times 26. 5 equals 26 minus 3 times 7. 2 equals 7 minus 1 times 5. And finally 1 equals 5 minus 2 times 2. Now, as before, we start with the last equation. 1 equals 5 minus 2 times 2, and the 2 we're replacing with 7 minus 1 times 5. So that becomes, combining like terms, we've got 5's here and 5's here. We've got 1 5 minus a negative 2, or plus 2 more. So 3 times 5 minus 2 times 7, and we do know that's 1, so we've done that correctly. We've used the 2, now we're moving on to the 5. I'm going to replace 5 with this. 1 equals 3 times 5, which is 26 minus 3 times 7. And then we've got minus 2 times 7. So we got 3 times 26, and then combining like terms, we've got 3 times negative 3, that's negative 9 times 7, minus 2 more, so minus 11 times 7. Now we want to repeat this process, this time replacing the 7. We've got 1 equals 3 times 26 minus 11 times 7 becomes 85 minus 3 times 26. Again, we're going to combine like terms. We've got 3 times 26, and then negative 11 times negative 3 is positive 33 times 26. So we've got 3 plus 33 more, or 36 times 26, minus 11 times 85. So we've got one more substitution to go. We're going to replace 26 with that. So we got 1 equals 36 times 26, which becomes 111 minus 1 times 85, minus 11 times 85. And we're going to combine like terms. We've got 36 times 111, and then we've got minus 36 times 85 minus another 11, so negative 47 times 85. Next, we're going to write that equation in the form of the linear Diophantine equation we're trying to solve. We get 111 times 36 plus 85 times minus 47 equals 1. Well, we don't want it to equal 1. We want it to equal 14,832. So we've got to multiply 36, negative 47, and 1, all by 14,832. When we do that, we get 111 times 533,952 plus 85 times negative 697,104, and that equals 14,832. So our general solutions are of the form x equals x naught, which is our 533,952, plus b, which is 85, over d, the greatest common divisor, which is 1. So that just becomes 85 times n. And y equals the y naught, negative 697,104, minus a over dn. And a is 111, d is 1 still, so minus 111n. Okay, so this is the form for all solutions. With this particular word problem, or any word problem in fact, we really want the positive values. It doesn't make sense, for example, that she walked into the bank with 533,952 US dollars and negative 697,104 of Canadian dollars. So the trick is to figure out the particular values of n that make both x and y positive. And we're going to need another screen for that. So here again are the equations for x and y, and our goal is to figure out values of n that make both x and y positive at the same time. To do that, the first thing we're going to do is set x equal to 0 and solve for n. And then set y equal to 0 and solve for n. When x equals 0, we solve for n. You get n equals negative 533,952 over 85, which is approximately equal to negative 6,281.8. If you set y equal to 0 and solve for n is approximately equal to 697,104 divided by negative 111, which again is approximately equal to negative 6280.2. Okay, so as n decreases in a negative direction, once it hits negative 6,281.8, x changes from positive to negative. As n decreases in a negative direction, when n gets to 6,280.2, y just changes from negative to positive. So all the values in between these two numbers, and we're only interested in integer values, will give us a positive x and y. So what are the whole numbers between these two values? Think about those on the number line. We want the numbers between n have to be less than negative 6280.2 and greater than 6281.8, negative. And what are the whole numbers between those? Well, there's only one of them, and it's n equals 6281, negative 6281. So we plug n equals negative 6281 into both of those equations. 533,952 plus 85 times negative 6281, and y equals negative 697,104 minus 111 times negative 6281. And solving those, you get x equals 67 US dollars and y equals 87 Canadian dollars. And you can plug those back into the original equation just to check and make sure this works. And in fact, 111 times 67 plus 85 times 87 equals the 14,832 that we wanted. So we found the solution. So one more linear Diophantine equation, and again, please pause the video and read the problem. Here our goal is to find the number of apples and the number of oranges purchased. So the equation we're going to have, now notice we're talking in cents and we're talking in dollars, and we don't want decimals. And we've got to use 1 unit, so we're going to convert to cents. So we've got 25x plus 18y equals 839 pennies. This is the equation we want to solve. So as before, step 1, find the greatest common divisor between the two coefficients, 25 and 18. So 25 equals 1 times 18 plus 7. 18 equals 2 times 7 plus 4. 7 equals 1 times 4 plus 3. 4 equals 1 times 3 plus 1. 3 equals 3 times 1 plus 0. The greatest common divisor is 1, and 1 divides evenly into 839, so we know there's a solution. Okay, next step, solve all those equations for the remainders. So 7 equals 25 minus 1 times 18. 4 equals 18 minus 2 times 7. 3 equals 7 minus 1 times 4. And 1 equals 4 minus 1 times 3. Now we'll use the extended Euclidean algorithm to get a linear combination of 25 and 18 equaling the GCD. So as always, we're going to start with the last equation. 1 equals 4 minus 1 times 3, and 3 we will replace with 7 minus 1 times 4 in the line above. Combine like terms. We got 4, and then minus a negative 4, so 2 times 4 minus 1 times 7, which does equal 1, so we're good. We've used the 3, now we're going to replace 4. 1 equals 2 times, new name for 4 is 18 minus 2 times 7, minus 1 times 7. Next, combine like terms. We've got 2 times 18, and then 2 times 2 gives us 4. So we've got negative 4 times 7 minus 1 more. So negative 5 times 7. And again, 2 times 18 minus 5 times 7 is 36 minus 35. That comes out to be 1. So we're good there. One more substitution. We're going to substitute in for 7. 2 times 18 minus 5 times 7 becomes the 25 minus 1 times 18. Combine like terms. And we've got 2 times 18, and then we've got negative 5 times negative 1. That becomes a positive 5. So we got 7 times 18 minus 5 times 25. So now we'll rewrite that equation in the form of our Diophantine equation we're trying to solve. So we want the 25 first. 25 times a negative 5 plus 18 times 7 equals 1. Now we want it to equal 839. So we're going to multiply negative 5, 7, and 1 all by 839. And the equation becomes 25 times negative 4195 plus 18 times 5,873 equals 839. So our general solutions are x and y. X equaling the x naught, negative 4195, plus v, which is 18, over d, which is 1, times n. And y is y naught, 5873, plus a, which is our 25, divided by the greatest common divisor of 1, so 25, n. Okay, so again, that's the form of the general solution, and we want to figure out the values for n that make both x and y positive at the same time. So as in the last example, we want to figure out first where x and y are both 0. What values of n make them 0? And those will be the values of n that make x and y change signs. So we've got, when we set x equal to 0, n becomes 4195 over 18 when you solve for n, which is approximately 233.05. When you set y equal to 0 and solve for n, you get n equals 5873 over 25, which is approximately 234.92. And as before, we want to figure out the value of n that is between these two values. So it has to be greater than the smaller number, 233.05, and smaller than the bigger number, 234.92. So we want to think about all integer values of n in this range, and there's only one of them, n equals 234. If there were more than one, then you'd have more than one solution to the problem. But n equals 234 is the one value of n that will give you both x and y positive. So now we want to plug those into the equation for x and y. So negative 4195 plus 18 times 234 and 5873 minus 25 times 234. And when you punch those into your calculator, you're going to get x equals 17 and y equals 23. So they purchase 17 apples and 23 oranges. And you should also verify to make sure that costs $8.39. So 17 times 25 plus 23 times 18, and that does in fact come out to be 839 pennies, or $8.39. So we've got the correct solution here. I hope that helps, and you have a great day.